Hey, welcome back to Linear Algebra. In section 1.4, we're going to take a look at some material about linear combinations. So you can see our objectives there. I want to define what a linear combination is. I want to discuss problems about finding whether or not a vector is a linear combination of other vectors and how that leads to a hopefully familiar problem about systems of n equations and m unknowns. Then we're going to take a look at a technical term. We're going to define what we mean by the span of a subset of a vector space. And in particular, we're going to show that that span is a subspace of V. It's always a subspace of V for any non-empty subset S of V. All right, so that's the objectives. Let's get going. Start down here with just an example to kind of motivate what I mean by linear combination. In the vector space R3, so let's take our field to be the field of real numbers, and we'll look at three tuples or ordered triples of elements. I've specified three specific vectors here. E1 is the vector whose first coordinate is 1 and the second two coordinates are 0. E2 likewise just has one non-zero coordinate, so 1 in the second position, and E3 and one non-zero entry in the third position. So those are three specific vectors in R3. And then if you give me a vector, I just picked this one, 2, 6, 8. I can write that vector 2, 6, 8 as a sum of scalar multiples of the vectors E1, E2, and E3. That's kind of easy to see in this particular example because if I take, say, 2E1, if I write E1's coordinates in there, and then I take, say, 6E2, these vectors E1, E2, and E3 are kind of special in the sense that because they only have one non-zero coordinate, when you scale them, you also only get one non-zero coordinate, and that non-zero coordinate is the scalar that you scaled them with. So the 6, because 6 times 0 is 0, I'll keep zeros in the second and third coordinate, putting a 6 in the first, and likewise. And now when you add these things together, say in the first coordinate, if I wanted to be very explicit, I'm taking 2, and I'm adding 2 zeros to it, but that doesn't give me anything different than 2. Same thing for the 6. In the last coordinate, I would have 0 plus 0 plus 8. And sure enough, that gives me the vector 2, 6, 8. So in the language that we're going to use, we're going to say that V is a quote unquote linear combination of these vectors E1, E2, and E3. I'm going to reveal the book's definition of linear combination below. I just clipped it out of the book because it's much nicer than my messy handwriting. But the idea of a linear combination is that, yeah, you take some vectors, E1, E2, and E3, you multiply them by some scalars, and you add those together. And any such result would be called a linear combination of the E1, E2, and E3. And since we could realize V this way, and V is a linear combination of those things. So let's make the formal definition. Taking it from the book, so it's printed nicer. So you got a vector space V, okay, and some non-empty subset of it. So we'll never speak about linear combinations of no vectors. So we at least have one vector, non-empty subset of V. Then we're going to call something, I'll highlight what he's defining. V is called a linear combination of vectors in S. If there exists, and this is important, I'm going to emphasize it, if there's some finite number of vectors in S. So it can't be an infinite number of them. He's calling them U1 to UN. And then the corresponding scalars, they have the same number of them. So U1 to UN are vectors. There's a scalar for every vector. And then here's the equation. V is written as scale those vectors U1 to UN by the scalars A1 to AN and add them together. So in that case, we'll also maybe just say that V is a linear combination of the U1 to UN, and these A's are called coefficients. It's familiar terminology of the linear combination. So a linear combination is literally a sum of scaled vectors in a given set S. This is just an observation here in the middle of the page that because 0 times any vector is 0, the 0 vector is a linear combination of any non-empty subset of the vector space V. All right, because you can always, if you have anything in this set S, you can always just take one element of S, multiply it by 0, and get 0. So the 0 vector is trivially, in some sense, a linear combination of any non-empty subset. Just to recapitulate our language above, our friend v equals 268 and R3, it was a linear combination of those vectors E1, E2, and E3 because we wrote it in that form. All right, lots of problems in linear algebra. That's what my little notation means here, LA, reduced to determining whether or not one vector is a linear combination of the others. LC is shorthand for linear combination. Many, many mathematical problems can be boiled down to asking the question, is one vector a linear combination of this specific set of other vectors or not? Okay. Let's look at an example that illustrates that. Here, I'm taking a bunch of vectors in R3. So all of these things are real number, triples of real numbers. So I'm going to assume they're vectors in the vector space R3. And I'm going to keep that same V, 268, and ask the question, well, is V a linear combination of these things? So what is that question asking? It's saying, can you find some scalars A1 through A5 so that when you multiply those scalars by these U's, I'm going to be a little brief here and just write dot, 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 A5, U5. Can we find them so that that's equal to V? Do there exist scalars A1 to A5 in the real numbers such that that equation is true? That's the question, is V a linear combination of these things or not? Well, how would we do that? It would require some computation. I've been a little bit lazy here, but I think you'll appreciate the better handwriting. Here's how we might start to answer that question. So like I was just saying, we have to try to determine if there are scalars A1 through A5 so that you can take the vector 268 and write it as a linear combination of those scalars. Okay, so that's the question we're asking. Can we find those numbers? Think of these things as unknowns. They're unknown elements of our field, A1 to A5, and we're wondering, could we find them? And then what's the author doing here? The author's just replacing, you can stop the video and scroll back up, but U1 was the vector 1, 2, 1. U2 is the vector -2, -4, -2, and so on. So the author's just substituting in everywhere. And then where does this equation come from? Well, it's just doing the vector arithmetic. So notice that like in the first coordinate, A1 gets multiplied by 1, A2 gets multiplied by -2, A3 by 0, A4 by 2, A5 by 3. That's what he's writing here in this first coordinate. 1A1, -2A2s, no A3s, 2A4s, -3A5s, and so on. So you do that for all three coordinates. And then, well, we can write, we can reorganize our information. This thing, oops, sorry about that, 268 is a linear combination of those U's if and only if these scalars, A1 to A5, satisfy this, the author's calling it a system of equations. Where does this system of equations come from? It's just from equating the coordinates of the vector. For example, the first coordinate here is a 2. Well, the first coordinate here is written as A1 minus 2A2 plus 2A4 minus 3A5. Well, that expression that's underlined, A1 minus 2A2 and so on, it has to equal 2. That's one of our equations. Yeah, and namely, it's this first one. I'm just setting that first coordinate. It's written right here in the equation. And I'm leaving a space so I can keep them lined up, setting it equal to 2. I'm taking the second coordinate, leaving space holders if necessary, and setting it equal to 6, because 6 is the second coordinate, and so on. So we end up getting what? A system of 3 equations and 5 unknowns. A system of 3 equations and 5 unknowns. And how do you solve such a system? In Math 241, you learned systematic ways to do this. In fact, you learned systematic ways to do it with matrices. I'm going to be a little less fancy here, and I'm not going to spend a lot of time walking through the details here. This is all taken from your text, but I just kind of want to hit the highlight of it. To solve this system, the author is referring to it just as equation 1, which is a very nice way, by the way, in your homework write-up. You write the system once, and then you can just give it kind of a number and refer to it. You don't have to keep writing it. So the big idea is to replace it with a simpler system that has the same solutions. And what does simpler mean? It means that you can read the answers off. Why does it have the same solutions? Because you do operations to it that don't change the solutions. like adding things to both sides of an equation, multiplying both sides of an equation by a non-zero number, replacing an equation with some multiple of another equation plus the equation, and so on. So to eliminate variables, so you want to eliminate the author, we're just going to walk through these one steps. So we're going to eliminate the A1 variable from the second and third equations. So how to do that? Well, to eliminate it, say, from this second equation, what are we going to do? We're going to multiply the first equation by -2 and then add the result of that to the second equation, because -2a1 plus +2a1 is no a1s, and so on. Likewise, you'll multiply the first equation by -1 and add it to the third equation to eliminate that a1. So the usual way of eliminating variables. In the resulting system, you can check the math. The other coefficients would end up looking like this. So maybe we can explain, like, where does this 2 come from? Well, we had to take -2 times the first equation. So that's -2 times 2 is -4. And we add that -4 to 6. Well, -4 plus 6 is 2, and so on. All right, so maybe in class we can work over this a little bit slower, but I'm assuming that for Math 241 it makes perfect sense. So the rest of this stuff I'm actually going to just really skip over. So we get this slightly simpler equation. A1 is eliminated from all but the first equation. And so now the author starts trying to eliminate A3 from, well, it's already eliminated in the first equation, so he eliminates it from the third one. All right, the next step is he's going to eliminate A4 from all but one of the equations. That's all but with the last one. So I'm just going to kind of skip over these steps. You can read them, but when you arrive at it, this is kind of the desired form. The desired form of that system. It's always obtained by replacing multiples of one equation with sums of another. It looks like this. And why is it the desired form? Because we can solve it for 3 of these unknowns. Just move the terms over to the other side, and we solve for A1, A3, and A4 in terms of A2 and A5, right? So these A2 and A5s are usually called free variables in the sense that you get to choose them. So the A2 and the A5 are called free variables in the sense that I get to select their values. And then anytime I select their values and replace them in here, these 3 equations tell me what A1, A3, and A4 have to be. So they're called dependent variables, right? So we can see that for any choice of A2 and A5, we get a solution. So it is the case that we can write 2, 6, 8 as a linear combination of these things. And if you want a specific linear combination, you just have to pick specific values for A2 and A5. Right? Here's the solution written out in general. And I think the author is, yeah, good. I would do the same thing. Pick A2 and A5 to be 0, the easiest values to plug in for them. And if you do that, then it will force A1 to be 4. Yeah, if A2 and A5 are 0, then A1, is -4. It forces A3 to be 7, and it forces A4 to be 3. So there is a solution in the sense that if we take A1, 2, 3, 4, and 5 to be those values, then that linear combination will yield our vector 2, 6, 8. So it in fact is. So that kind of process illustrates in general, when you're trying to decide whether one vector is a linear combination of some other set of them, a finite set of them, in general, that leads to at least for vectors written as these n-tuples, that leads to a system of equations. And you can use that variable elimination technique that you learned in Math 241 to see if that system has a solution. And if it does have a solution, then your vector is a linear combination. If it doesn't have a solution, it's not. We're going to study this process in detail in this course as well. It kind of comes later in chapter 3, so I'm going to leave it at this conversation level now. But please do have a careful read of example 2. Starts on page 28 in your book, and make sure you can follow the computations in there. Make sure that those steps make sense, because there the author is doing the exact same thing I just did, but he's doing it in the context of a polynomial. So you're getting used to sort of what the system of equations would pop out, but it's the same kind of idea. You get a system of equations that you then solve by that systematic elimination technique that you learned in Math 241. We'll circle back and discuss this kind of more generally in chapter 3. But for right now, I'm just going to move on. Okay, so that's kind of our first objectives. We've defined what we mean by linear combination. We've talked about how a linear combination problem leads to a system of equations. So now I want to talk about this very important vocab word called the span. The span. So if you give me a non-empty subset, it's important. S is some non-empty subset of a vector space V, then the span of it is by definition the set of all linear combinations. Set of all linear combinations of the vectors in S. So any vector that you can get as a linear combination of vectors in S goes in the span. And if you're in the span, then you must be a linear combination. So for example, let me kind of squeeze, let me squeeze in an example before my example here. 2, 6, 8 is an element of the span of the set that consisted of those vectors U1 through U5. How do I know that? Because we just wrote 2, 6, 8 as a linear combination of those vectors. And so that by definition, it's in its span. Anything inside the span of these vectors would be a linear combination of them. All right. As a second example here, again in R3, if I took the set to be, say, just the two vectors, E1 and E2, defined earlier in the lecture, so 1, 0, 0 and 0, 1, 0, then its span, well, it's the set of all linear combinations of those things. So I take any scalar alpha and multiply it by E1, any scalar beta, multiply it by E2, they're arbitrary. And if you simplify that, you'd get something like this, alpha comma beta comma 0. So that's a description of the span of those two vectors. And you can check with the subspace test that the span of that set S is subspace of R3. Yeah, this set contains the 0 vector. Take alpha and beta to be 0. You add things of this form, you get something of that form. You scale things of that form, you get something of that form. So it satisfies the subgroup test. 1, 2, 3 conditions are true, so this thing's a subspace of R3. You can kind of recognize it from calculus. It's the subspace of R3 that kind of corresponds to the XY plane. It's the points in space whose third coordinates are all 0. Right? The theorem I want to prove in this section says that for any non-empty subset S, the span of that set is going to be a subspace. So I'll slow down a little bit here because I haven't written the proof of this theorem out. The proof is written in your book. So if you prefer, you can just read the author there. It's going to be written kind of cleaner and in better notation. But I want to kind of walk us through here in real time. So what are we asked to show? That the span of any subset of a vector space is a subspace. Here, the author is kind of using this convention. I skipped over it. Sorry, I'm going to scroll back into the definition. If you want to include any subset of a vector space, and you don't want to have to keep saying non-empty, then you can just define the span of the empty set to be the set that contains the 0 vector alone. All right, the set that contains the 0 vector alone is a subspace. So if the set happens to be empty, then the span of it is a subspace by declaration, by default. Okay, so that's why in the statement of this theorem here, you don't see the author talking about any non-empty subset. We can say any subset, but we have to kind of treat that as a special case. So that's how I'm going to start, is by saying, well, if S happens to be the empty set, then its span, by definition, is the set that contains the 0 vector alone, and that's a subspace. So we may assume, it's a nice acronym in chalkboard proofs, we may assume that S is not empty. Okay, so I have to show now that the span of S is a subspace. I have to use the subspace test. So I need to have the 0 vector in there. Well, if S isn't empty, there has to exist some vector V in S, right? Because it's not an empty set. And if I take the 0 scalar and I multiply it by that vector V, I get the 0 vector, right? But the 0 scalar times V added to nothing else is by definition an element of the span of S, because V is in S. So that shows that the 0 vector is in the span of S. All right, so that's the first of our three conditions that we have to check. The first of our three conditions that we have to check, that the 0 vector is in there. The second condition is the closure under addition. So I need to take two vectors. Let me call them X and Y, just like in the definition. So take two vectors in the span of S. All right, my goal is to show that their sum is. My goal is to show that the sum is in the span of S. So we have to write down, well, what does it mean to be in the span of S? If X is in the span of S, then there have to be vectors in S. I think I'm going to call them U1 to UN. Oops, and scalars. Say A1 to AN in my field, such that X is equal to A1 times U1 plus and so on up to AN times UN, right? So likewise, that's kind of a lazy word for I don't want to put in all of the details. Likewise, Y has to be some sum. I'm going to call it, say, B1. Maybe I'll call them V's. B1 up to, say, BM, VM, where the VJs belong to the set S, the B sub J's belong to the field, right? Because Y is in the span of S. That's what I mean by this likewise. It's the same exact reasoning that I do for X. Okay, well then if we add X and Y, you add these two linear combinations, just stick them next to each other, AN-UN plus B1-V1 BM-VM. And now look at that thing. The U's and V's are all in S. The A's and B's come from S. This is an element of the span of S by definition. It's a linear combination of elements of S. Right, so the second part of the proof is something to keep in mind, that the sum of two linear combinations is a linear combination of elements of S. Good. All right, finally, so that's the second condition. Finally, if we take any scalar alpha and we say multiply it by our X, well, you're just taking alpha and multiplying it by this sum, A1, U1, plus and so on. But we have, sorry about that, that's a V. UN, by the distributive law in the vector space. That's alpha A1 U1 plus and so on, alpha AN UN. And certainly alpha AI belongs to F for all I. So this thing is also an element of the span of S by definition. All right, so that's the first part of our theorem. This shows that the span of S is a subspace. All right, I have to scroll back while I talk about it because I didn't say anything about it in the first part. Sorry about the scrolling. But there was a second statement of this theorem. The author says that any subspace of V that contains S has to contain its span. All right, so what's that saying? That's a little bit more subtle. It's saying if you have some other subspace and every single vector in S was in it, then any linear combination of those vectors would be in it. So to prove that, scroll back down here. So let's suppose that W is a subspace of V, and that S is a subset of this W. Okay. So what do we have to show? We have to take any element of the, we want to show, another nice acronym, want to show that the span of S is contained in W. Well, so this is, again, a kind of a standard mathematical situation. I want to show one set is a subset of another. So I do that with a so-called pick-a-point proof, right? So I pick some x, in the span of S. We already have some notation for it. I won't even requantify it all. X is some linear combination. Coefficients are called A's, the vectors are called U's. Yeah, some linear combination. These A's come from F, the U's come from S. But every one of those U's is also an element of W because S is a subset of W. Every element of S is in W. So if UI is in W, say let's pick on U1. If U1 is in W, well, so is A1 times it because W is a subspace. Yeah. AI times UI belongs to W for all I because W is a subspace. Right? But then W is closed under sum. So X is an element of W. Right? So what was X? X was any element of the span, and we've been able to show that it's in W, so that shows that the span of S is in W. All right, so if you put those two things together, that the span of S is a subspace, and it's contained in any subspace containing S, then you can kind of say, okay, well, the span of S is like the smallest subspace of V that contains all the elements of S, because any other subspace that contains all the elements of S contains this span. It's kind of a useful way to think about it. Okay, we're getting close to the end here. This lecture is also pretty long. So let's try to wrap it up with looking at this one more definition. So we're going to say that a subset rather S of a vector space generates the vector space if its span equals the whole vector space. Okay, so we've just seen that spans are subspaces. If that span is the entire vector space itself, then we're going to say that S generates V. We also can say S spans V. Okay, so generates V and spans V is the same thing. It means the span of the vectors is the whole vector space. So for example, if I take the set S to be the vectors E1, E3, E2, and E3, they span R3. They generate R3. Because if you take an arbitrary vector in R3, an arbitrary vector in R3 looks like A1, A2, A3, so some three tuple. Well, I can write that as a linear combination of the E's, just taking the coefficients to be respectively A1, A2, and A3. So that set spans R3. Here's an example out of the book. This author's giving three vectors again, but they're 1, 1, 0, 1, 0, 1, and 0, 1, 1. And he's saying they span, they generate R3 as well. So in order to prove that, again, you'd have to show that an arbitrary vector A1, A2, and A3 has to be some linear combination of them. So you'd be looking for scalars. He's calling them R, S, and T, so that R times the first vector plus S times the second plus T times the third is your arbitrary vector. And then the author just kind of claims, well, okay, yeah, take R to be this, S to be that, T to be that. So how were those scalars determined? How were those scalars determined? Well, by solving a system of equations. I'm not going to do it here in the lecture, but yeah, those things were, well, what system of equations? It all comes from here, looking at the three coordinates. For example, if I just did a little bit of math, if I pushed this R through there, I would get what? R, comma, 0. This one would be S, comma, 0, comma, S. This one would be 0, comma, T, right? And that has to equal A1, A2, and A3. Well, if you add, say, the first coordinates, R plus S plus 0, that has to be A1. That's your first equation. R plus S has to be A1. The second equation says that R plus T has to be A2. The third equation says that S plus T has to be A3. And then using that elimination technique that we talked about a little bit earlier in the lecture that you saw in Math 241, you could solve those equations for R, S, and T, and these are the three values you're going to get. And since A1, A2, and A3 are any three numbers, that determines this R, this S, this T, then any vector is in the span of those sets. So that set generates R3. Okay, there's some other examples in your book about matrices and polynomials. I'd suggest that you take a look at them, read them carefully about these spanning sets. But that's where I'm going to cut this one off for the video lecture. Thanks for listening.